3D scanning is a rapidly evolving field. In recent years, there has been a revolution and a massive surge of interest in this area due to the innovations in the field of 3D scanning, such as neural radiance fields and Gaussian splatting, NeRFs and G-splat for short, respectively. In this video, I'll show you how we use 3D scanning to quickly create highly detailed 3D reconstructions to aid in rapid prototyping, documentation practices, and more. When we build a vision system for quality control, it has to fit on a production line, and that requires us to have a spatial understanding of the production line and its dimensions so that we know where to place cameras and light fixtures and more. This can sometimes be slightly a cumbersome process to communicate back and forth with the customer. But thanks to the recent innovations in 3D reconstruction, we can now very quickly create a highly accurate 3D model of a machine that we can use in our rapid prototyping process, for example, when we're investigating various solutions for our customers. When we create a 3D model of this, for example, we can send it out of the door, and then in 5 years from now we can have this visual timestamp of how the system looked when we sent it out of the door, even though it's currently in China or somewhere far away. Previously, 3D models were created on a rather old technique called photogrammetry, which makes use of classical stereo vision techniques to create 3D models from 2D images. But even though NeRFs and G-splats still rely on these 2D input data from various angles, they function rather differently from photogrammetry. In the case of NeRFs, for example, the method is instead based on mathematical models of how light propagates through space and interacts and reflects off surfaces. And in the case of G-splats, it relies on a very clever use of rasterization, computer graphics, and gradient descent, which is also used in deep learning, to render scenes in 3D. G-splats also often surpasses NeRFs in terms of speed and quality, which makes it the current preferred method at JLI for reconstructing things in 3D. The technology opens up many possibilities, like using these 3D models of our customers' production lines to investigate if there's room for cameras or light fixtures, for example. Instead of spending a lot of time in the factory and disrupting their production, we can make a video recording in less than a minute with our phones, which we then turn into a NeRF or G-splat subsequently. A digital copy, or digital twin, if you will, that we can take back to the lab, and from here we can develop our solution. We quickly see if there is room to place various things in various places. All of this allows us to test different solutions faster, and therefore we arrive at the best solution for our customers more quickly. Furthermore, the technology can also be used in documentation practices, which gives us this visual timestamp of how a system looks before we send it out of the door. And this is on top of all the other usual internal qualification tests that we usually do. As mentioned, the development and progress of 3D scanning is currently progressing at an extremely fast rate, with new research papers and methods being published almost on a weekly basis, comparable to the rapid innovation and interest we see in large language models such as ChatGPT, for example. Since it is a priority at JLI to always push the frontiers of the latest technology, we are following along in this exciting field, and we are currently investigating new and innovative solutions using this technology.